Hey everybody, we're gonna start our 4 component lessons on evaporators. So if you'll go to the evaporators module, and there's a couple of PowerPoints there. This actually follows along with chapter 21 in your book, so you can check out some stuff there as well. All right, so I'm gonna pull this up first. All right, so you'll have to excuse me. I've got a little bit of a cold, but we'll be fine. So we'll get through this, hopefully. So as we've learned through the refrigeration cycle, heat is picked up through the evaporator. So in ACR 100, and even in our review in this class, we talked about the function of each thing and a little bit of the nuts and bolts of each one. But up until now, we've kind of kept it pretty general. We've pretty much stayed just under the assumption that an evaporator is just something that absorbs heat, and that through the absorbing of heat, most of the time it's going to absorb heat into the refrigerant. The refrigerant's going to boil off, and you're going to have 100% vapor coming out before you go to the compressor. So up until now, we've kind of just sort of said, evaporator is an evaporator is an evaporator. So the cool thing about this class is we get to take the general things and we get to dig into them a little bit more. So these next 4 lessons will be evaporators, condensers, compressors, and metering devices, broken down a lot more in depth. So how do you troubleshoot them? What can go wrong with them? How do they operate? What are different types of each of these things? So they're not just all exactly the same. So before we get started, a couple of things that hopefully you're familiar with is the function of an evaporator. The function is to absorb heat and to collect moisture in most air conditioning setups, and this also applies to refrigeration. Basically anything that we're using a direct refrigeration coil across air. Now, when we get into water cooling, chillers, which we will talk about maybe a little bit through this lesson, that changes a little bit, but it's just the removal of moisture, removal of humidity, moisture, and changing temperature. So collecting heat. A few terms that hopefully you understand: TD and delta T. Hopefully you understand the difference in those. So you understand that TD is, and I get these confused myself sometimes, but TD is how much colder your saturation point is than the medium around it. So if it's air, how much colder is it than the indoor air? So for a home, residential or commercial HVAC, comfort cooling, we usually operate under a 30 to 35 degree TD, which means if it's 70 to 75 in the room, you're looking for like a 40 to 45 degree saturation temperature. And then your delta, that's your temperature drop across the evaporator. So supply air and return air compared to each other. So how much colder is the supply than the return? How much temperature am I removing? And then how much moisture am I removing as well? Which is a little harder to calculate because you can't just put a thermometer and calculate moisture. Superheat. Hopefully you understand what superheat is and how we measure it. So you measure superheat by sticking a thermometer, some sort of temperature probe, to the suction line, and then measuring your saturation temps with your gauges. Subtracting those two together, so you take your saturation temp and your suction line temp. Your suction line temp should be higher than your saturation temp, and it should be roughly 8 to 14 as a general rule, especially if you're working with a TXV, thermostatic expansion valve. And then if you're working with the fixed orifice, hopefully you can learn how to calculate target superheat. So we may review that as well in class. Excuse me. And then effects of heat load on the evaporator. So the more heat there is in the room, the more moisture there is in the room, it's going to change things. All right, so the original ones were just pipes. There was no fins, there was no airflow. It was just natural attraction. And actually, there's some systems that still use a form of this today. There's a system in some of the school systems called a chilled beam system, and it uses something similar to this, and it's just using a cold, no air blowing across it, just a cold surface to attract heat. So kind of cool. But the fins do a few different things. The fins are metal, so they become more surface area. They increase the surface area that's colder, but they also slow down the air. So those fins, they're not just a straight shot. A lot of times they're kind of made in such a way that the air has to kind of work their way through them. And so by doing that, you allow what we call dwell time. And dwell time is just how long that the uh, the air has across the evaporator. So when you're trying to remove heat from something, you kind of want it to be in contact with it for a little while. So you don't want to move air too fast. Same goes with water. When we get into water cooled systems and systems that use water for cooling and heating, if you move the water too fast, you'll actually bypass a lot of the heat transfer because you don't give it time to dwell. So the same thing goes here. So you kind of have to slow that down a little bit. Same goes for air, blowing air across your coil with your blower. If you just speed that up as fast as it'll go, you'll actually lose performance. So running it as slow as you can get it sometimes is better, as long as you can still keep up with demand. All right, so single coil evaporator. This is kind of similar to what we've talked about. Refrigerant enters, refrigerant leaves. A lot of ours that we're going to deal with are going to use some sort of distribution tubes that's going to actually create multiple circuits within it. So a lot of our setups have this to where it's not just coming straight in like the last one and it's just going all the way through. It's actually breaking the coil down in smaller circuits, multiple circuits, and splitting the refrigerant up so it can remove more heat quicker, doesn't, more efficiently. So liquid comes in, goes through the TXV, it's broken down and then split up into, in this case, four, and then that's sent through each channel or each circuit, and then each one of those is coming back to a header, and then that header is full of suction gas at that point. So something that could happen here is if you've got multiple passes or you've got multiple circuits, you could have an issue with one of these distribution tubes. And while I'm on the subject, a lot of people will call these capillary tubes, and they're actually not. They're distribution tubes. They're distributing refrigerant to the condenser or to the evaporator or to the condenser. So it's not, the term capillary tube actually refers to a type of metering device, but they do look a lot like a capillary tube. So these can get stopped up. These are really bad for rubbing holes in each other to where you'll have rub outs for leaks. So this is a good place to check for leaks. So if you have one of those that's underfeeding, it could be because you have a restriction in one of those. All right, so hopefully we know this by now, that we're taking warm air, we're absorbing heat, and we're putting it in the refrigerant. Latent heat, if you remember this, latent heat is the heat required to change state, but not temperature. So boiling, freezing, thawing, condensing, evaporating, all those are terms for latent heat. Sensible heat is a temperature change, something that's measured with a thermometer. And I've always said sensible heat makes sense, right? And we're going to use sensible heat. Superheat is sensible. It's degrees above saturation. Saturated refrigerant is anytime you have liquid and vapor together in an evaporator, you're going to have a saturation point. Is a saturated liquid, saturated vapor. Sorry. And then the saturation temp is just at a specific temperature, at a specific pressure, the refrigerant is going to saturate at a specific temperature. evaporator temperature, suction temperature. These are all just the same names for saturation temp. All right, so your basic function, this is using an R22 system, it looks like. Yeah, it is. You've got about 70 psig, which is about 40 degrees. You got a 75-degree return air, 55-degree supply, which means your delta is 20. Your saturation temp is 40 degrees entering the condenser or the compressor. And that's all on your low side. All right, so how do you measure evaporator temp? So if I were to say, what is the suction pressure or suction temperature? What is the saturation temperature? What is the evaporator temperature? What is saturated suction temperature? VSAT, call it whatever you want to call it. If I say how cold is the evaporator, I'm not referring to the physical temperature of the evaporator. I'm referring to the saturation temp of the refrigerant inside of it. So how do you measure it? You put a set of gauges on it. You find your pressure. You convert that pressure to a temperature using a PT chart. If there's one provided on your gauges, you use that. Or digital gauges, you got those. Or find a PT chart or use an app or something. So you're just converting that to its saturation temp at that pressure. So in this example, R22 at 69 pounds is 40 degrees. But if this were R404A, the same pressure would be about 29 degrees. 134A would be 68, 69 degrees. So just looking at that different charts at the same pressure, you got to make sure you're checking the right refrigerant. All right, evaporator TD, space temp minus the evaporator temperature, or space temp minus or saturation temperature, right? Your suction saturation. So why is TD important? Well, for one, you kind of need to know what type of system you're working on. So up until now, we've operated under the assumption that everything is 30 to 35 degrees cooler, every evaporator. As we go on through this class, but more so through your commercial refrigeration class, we talk about low and medium temperature applications. You'll actually see that that's not always the case. So for air conditioning, comfort cooling, we're going to operate under a 30 to 35 degree drop, TD. But when we change systems, sometimes that may change as well. So air conditioning is going to operate under the assumption of a 75-degree space, 40-degree evaporator for a TD of 35 degrees. Subtract those two. A reach-in cooler, and these are kind of just some general, you can actually get a lot more specific than this. And I would always refer to manufacturer's information versus this generic thing, but kind of gives you an idea. A reach-in cooler, your evaporator temperature is going to be colder than the space. So if the space has to be 40, you're going to run an evaporator temperature somewhere around 20 degrees, which means you're going to be running about a 20-degree TD. Some on a walk-in, those tend to run a little bit lower. And I'm assuming they're calling that a walk-in cooler, yeah, because your evaporator temp is 25 and your space temp is 35. So freezers as well, low temp applications, you're going to run more like a 10-degree TD on that as well. All right, so most of your air handlers are using an upflow configuration, which means they're pulling or inducing air through the coil by the fan being on top of it, pulling it from the return into the supply through the coil. So your coil's under a negative pressure. In the case of furnaces and maybe some other types of air handlers, the coil may be after the fan. So if that's the case, it's under a positive pressure. That's a forced type setup. So that does make a difference, and that can come into play. And it also makes a difference here, like where you see that they're actually cleaning that evaporator, first of all, you're not going to see what they're seeing without taking, usually there's a little metal triangle on the front of these coils. So you're not going to see that without taking that cover off. If you do, that's an issue in and of itself. So it has to be forced, pulled through that coil. So there can't be a way that it can get around it. So with that triangle being out, obviously it's going to be able to get around it. Cleanliness is probably the biggest issue with evaporators, honestly. TXVs can cause them not to work right. If the TXV is not working right, charge is an issue as well. But honestly, the evaporator itself, like the biggest issue with an evaporator itself that you're going to have to deal with is probably cleaning, maintaining, checking for cleanliness. And so the hard part of that is a lot of times you can't see, you can see the top of the coil, but usually the top's going to be pretty clean. So unless it's like a mobile home that has a coil sitting on top of it and it's pulling it down, it's a downflow. Usually you can't see the return side of that coil where it's actually pulling the air into. So you'd either have to take that cover off like they've done here, or if you can take the door off and see underneath of that coil, but most of the time you've got a line set hooked up and pipes and other things hooked up. So it's usually pretty hard to do that. Sometimes you can look in the filter slot if you can look underneath of it that way, and see what kind of shape it's in. Or if you learn how to do your static pressure readings, which is something that honestly I'm not as awesome at as I'd like to be, you can use those static pressure readings to measure static pressure difference across your coil and pretty much tell you if your coil is clean or if it's stopped, if it's somewhat stopped up. So check your filters and then check the coil itself as well. So especially if you've got a filter that's really dirty or it's not a very aggressive filter, you're going to want to check that coil if you suspect because of your readings that you're low on charge. Or if you're doing like a system check every 6 months or so, not a bad idea just to peek at that evaporator and make sure that it's clean. A lot of times they can be brushed off, cleaned off pretty easy in place, but if they get really bad, you're going to have to take that bad boy out and clean it. So that's not something you want to do if you can avoid it at all, because then you got to pump your system down, cut your line sets, pull your coil, go outside, cleaner on it, water hose, use an acid or some sort of high-powered cleaner, solder it back in, pull a vacuum. So you're talking about a pretty big process. So maintenance is a big deal. Filters is a big deal. Different types of evaporators. These are what be used in like walk-ins and reach-ins. They just hang from the ceiling, so they're a little different. They're like a fan coil. They have fan blades instead of a blower. Not going to spend a ton of time on this. Just what we talked about a while ago. Just different temperatures of different conditions. So for air conditioning, we're operating under a 35-degree TD, 40-degree coil at 75 degrees. Now, obviously, if the inside is not 75, then your evaporator temp will change and your TD should remain pretty much the same. Now, humidity can play a factor in that. If you got a lot of humidity, sometimes that'll cause your TD to go down. So instead of having a 35-degree TD, you may run 28 or 30 because a lot of that coil gets loaded up with moisture, and then you're not reducing the temperature quite as much under a very humid pull down. All right. So, like I said, without getting too far into commercial type setup, AC, we're usually trying to operate under a 35 degree TD with a 50% humidity in the house. That's kind of normal operating conditions. So not only are we concerned with the temperature of the room, we're concerned with conditioning the air. We're concerned with the comfort of the room. So there's actually a lot of information that shows that if you reduce the humidity in the summertime, when it's humid outside and when it's humid in the room, you reduce the humidity a little bit and you get it a little bit drier. Now, you don't want to dry it completely out, but you get it 40 to 50%. You can actually run your thermostat higher because your temperature doesn't have to be as low because you don't feel as hot. That humidity makes you feel, everything feel damp, everything feel clammy, and makes you feel warmer. So if you can dry that room out a little bit, it'll actually help evaporate the moisture from your skin, kind of like a fan blowing across you. Even though the fan is just blowing the temperature of the air in the room, it creates this evaporative cooling effect. So you want that humidity to be right. If you're running anything over 55%, 60%, you're getting in danger of creating mold and not healthy air. So the higher the TD, the more moisture that's removed. So there is one philosophy that says if you're trying to remove more moisture, one of the things that I've done in the past is actually slow down the blower. Now, you don't want to just guess at this. Like, you want to kind of have a good idea of what you're doing, because you want to know that the blower at that speed will still keep up with demand. But usually I like to run the blower as slow as I can run it and get by with it. So like at my house, you don't hardly hear the blower run. I don't like to go in a house and you have to turn up the TV every time the air conditioner comes on. That's not the way that it should be designed. So it shouldn't bounce the curtains and blow your hat off your head when you walk in the door. Even though some people like that, it's better if you don't even know that it's on. So that's what we're shooting for. Slow it down, have enough capacity, still make sure that you're not flooding back liquid. So if you slow it down, that's going to affect your heat transfer. That's going to affect your superheat, and that could affect your liquid flood back. So you got to watch that. You can't just go in and slow it down and just leave it. But if you can toe that line a little bit, you can actually run a little bit colder coil than normal, which allows you to pick up more humidity. It probably means your system's going to run longer, but it allows that system to run longer, which means it's going to remove more moisture. So by being colder and by running longer, it's going to dehumidify your room a lot better. Reach-ins, walk-ins, coolers, freezers, that stuff, they actually run at higher humidities. And for food production, food storage, different foods are supposed to be stored at different temps and different humidities. So actually you don't want those foods to dry out. You want it to stay pretty humid in there. So that's another reason why they run lower TDs in coolers and freezers, because they don't want to dry it out. They want to take a pound of meat, stick it in the freezer, freeze it solid as quick as they can, but retain all the moisture. You don't want to dry out the food in the refrigerator. All right, so how TD affects humidity. Obviously the higher the TD, temperature difference, like we've talked before, the more moisture that you're going to collect. Same way with your TD across our water bottles that we did way back, going to collect more heat and collect more moisture. And then if there's a latent change, it's going to speed that up even more. TD versus delta. So TD is your temperature difference, which is your air entering the evaporator or your return, minus the refrigerant temp inside. And usually that's 30 to 35, 35 degrees, let's say. Delta T is your return minus your supply. And that's going to be 18 to 22 is where I kind of like to hold that. Like I said, it's going to vary, but so they're averaging it at about a 20-degree delta, and that's fine. All right, so they're just showing you how they're measuring a TD and how they're measuring delta. So they got return, supply. I guess there's a coil in the middle there somewhere, or, well, that looks like a downflow, upflow setup, return and supply. Superheat, hopefully we know what this is. We know why we measure it. There's actually going to be two ways that we measure it now and going forward, especially in commercial refrigeration. When we get into freezers and stuff, we need to measure both of these. So there is total superheat or compressor superheat, which is going to be measured outside at the outdoor unit. And then there is evaporator superheat, which is going to be measured at the outlet of the evaporator. You can't always do this, but especially in commercial setup, you're going to try to take both of these readings because your line set starts to really come into play. If you have a extra long line set, if it's not insulated very well, or even if it is, maybe it's going out on a roof where it's really hot or really cold. Maybe it's going through an attic, or it's going through another freezer or another cooler, or a mechanical room that's really hot. If it's picking up excess heat, that heat's going to go to that line set because it's colder, just like anything else. And so you're going to pick up additional superheat. So um, when we measured at the outdoor unit, that's actually more like measuring what we would call total superheat or compressor superheat within 6 inches or so of the compressor. Obviously, we're a little farther than that when we're on the outdoor unit. But if you're actually wanting to measure evaporator superheat, that's going to tell you the exact conditions of your evaporator, and then you could compare those two together to see if you're picking up too much heat through your line set. So there are some disadvantages of having too higher superheat because if you're trying to shoot for 8 and you have 8 outside, you probably don't, if you're picking up a ton of heat through the line set, you probably don't have 8 at the evaporator. And then on the flip side, if you measure at the evaporator and you measure 8, and then your line set's completely uninsulated, by the time it gets to the outdoor unit, you may have 30 degrees superheat because it's running across a roof or through a hot room. And so that excess superheat gets transferred into the refrigerant, which then gets transferred to the compressor. That compressor has to be cooled by that suction gas. And so if it gets above, and you'll hear me talk about this in compressor unit, if it gets above 65 degrees, most compressor manufacturers say that's as high as you want that gas temp to be. So if you've got 40-degree refrigerant temp and 25-degree superheat, then you're at 65. So you've got to try to keep that extra superheat down in that line set. And if that means additional insulation or whatever, then that may be what you got to do. So hopefully at this point we know what superheat is. It's just excess heat that is added beyond saturation. It is sensible, so it's measured with a thermometer, and it's measured by comparing the line temperature to the refrigerant saturation temp on the evaporator. So in this example, we're going to measure the line temp and compare it to the 40-degree saturation temp. So you're going to have a 10-degree superheat. Hopefully that's a review, but if not, that's fine. Now, slide on over to the left. You'll see they're measuring at the inlet of the compressor. They're measuring 60 there. So compressor superheat or total superheat is actually 20. So depending on where you're measuring it, you may get two different readings. So evaporator superheat is telling you just what's going on inside of the evaporator, line set not included. Total superheat is factoring in the line set. And both of those are things that you might want to know. A lot of guys in residential aren't really measuring that. If they're measuring any superheat, they're probably ahead of most. Or if they know how to read that and interpret that, that's good. But when it gets to more commercial, more finicky equipment, I would really want to know what both of those are. So why do we measure superheat? Well, a few different reasons. One, it helps us to determine how efficient the evaporator is running in the first place. Tells us how much liquid refrigerant or evaporating refrigerant that's going through a latent change. And then because that's where all the work's done, right? So the evaporator does most of its work while it's evaporating refrigerant, not after it's evaporated. So we want just a little bit of the coil to be under latent or sensible change, but not much of it. So we want to make sure that we're leaving the coil as 100% vapor, but we don't want the majority of the coil to be under 100% vapor because it just doesn't pick up a lot of heat. It doesn't have much capacity. Average, like I said, 10 degrees, kind of a good average, and then 5 to 20 may be acceptable. You could have more than that, depending on if it's a fixed system and you're running, different conditions. Your target superheat should tell you that. Superheat's too high, so if it's above your desired, it tells you that it's starving. And so what do you do about a starving evaporator? It means that it's getting rid of its refrigerant too soon, which could be a number of things. It could be caused by low charge. It could be caused by a restriction in the TXV. It could be caused by too much load in the house. It's really hot. But that's why you would need to understand all those factors. Do we have this for this? And then you would need to line all those up to say, does everything else indicate that it's low on charge, or is it something else? So that's where your little troubleshooting charts come in to say, what are the symptoms of X, Y, and Z. Superheat too low, it's flooded. So if it's below 5 degrees, flooding evaporator means you're not evaporating refrigerant like you should, so you're in danger of flooding back to your compressor. So that's usually a low load situation, low airflow, dirty filter, dirty coil, TXV open too wide. Now, if you have the ability to do it, like a commercial system may have an evaporator's suction port. Most residential setups don't have that. So, we don't really have that ability to just go inside and grab a port in there. If you do, that's great. You can get a pretty good idea just by measuring your pressures outside, because that pressure really doesn't change a lot during that superheating, or it shouldn't really change at all outside. So once it becomes 100% vapor, that shouldn't change a lot. So your suction temperature should be pretty much the same. So you could use your outdoor pressure, convert that to a temp, and go inside and strap a thermometer to the line inside the unit and measure evaporator superheat. This would be more the case like, if you were getting really high superheat outside, but you had a long line set and you were trying to determine if it's just from the line set issue or if you actually have a problem with your system itself. Kind of point you in the right direction. All right, so high load, low load. If you've got like a hot pull down, you got a room that very, very hot. It's been down all day. You get it fixed. It's 85 degrees in the house. You're going to still follow your TD more than a desired supply temperature. You're going to try to follow the TD. So you're going to say, well, I know at this condition, I should be running about a 20 degree. Not TD. Well, your TD and your delta. So if it's 85 in the house, I'm looking for about a 20 degree drop, give or take. So I could pull that down to 55, 85 in the house. I could pull that down to 65. So I could drop the temperature of the refrigerant by 20, give or take 18 to 22. And then I would look at my refrigerant pressures and I would say, okay, I'm still going to go by my indoor minus 35. So if it's 85 and I subtract 35, I'm maintaining that TD. So now I'm looking for a 55 degree saturation temp instead of a 45. So that's where if you just say my gauges should always read 45 or always read 40, you're going to run more like 50 to 55 versus 40 to 45 on normal conditions. But if you just charge it to 40 and you say 40 is where I want to be, then once that room gets pulled down, that's going to drop more, and now you're going to still be undercharged. So you got to take all that into consideration. Too little heat, low load, it's going to lower your evaporator temperature. So like in our lab, a lot of times we're dealing with low load situations, and it lowers our pressures to where we're running more like 38 and 37 instead of 40 to 45. So just the nature of the beast. And it also affects your head pressures as well. Load may affect superheat. Depends on the amount of load and the metering device used. So if you've got a TXV, the TXV is going to try to keep up, and it's going to open or close based on load. If it doesn't need as much refrigerant or if it needs more, it should adjust for that within reason, unless it just is doing all it can do. Or if it's got another issue. So if it's got too much load and low charge, then it's probably not going to be able to keep up. That's what we just talked about. So on a startup, you got 85 degree return air. Superheat's a little high, but that's probably normal. You're running a 50 degree instead of a 55, or instead of a 40 degree coil. You're running high superheat because you got a lot of heat available. So you got the same amount of refrigerant, but you're trying to do more work than normal. So obviously those readings are going to be off for a while. But as it runs and runs and runs, it should pull everything down to the right numbers after a while. So you shouldn't have to stick around and wait for it to get there. As long as you factor in what's going on now, you should be able to leave and it should be fine. So follow your TD, follow your delta T. So now your load's dropping. Now we're at 45 and 80. TD's pretty much remaining the same. Delta T's pretty much remaining the same. Superheat's straightening out. Now we're down to 40, so everything should, come back to normal. All right, so I want to pull this other one up here real quick and just glance through that and see if there's anything else I want to pull out. So really, the biggest thing you're dealing with, honestly, in residential especially, and even most commercial stuff, on the evaporator itself is just keeping it clean. You don't want stuff growing on it. You don't want stuff sticking to it, dirt going through it, clogging it up. Keep your filters changed. Keep everything inspected good. Keep it all cleaned off. Make sure there's no leaks in it. That's something that can happen to them. But everything else is a byproduct of the rest of the system. So if you're low on charge, that's going to affect your evaporator. If something else isn't working right, it's going to affect your evaporator. But the evaporator itself is just a coil. It's just a coil of metal, so it shouldn't really have a lot going on with it as long as it's clean and it's getting air to it. So I want to make sure there's nothing else in here I want to. I think that's about all we need to deal with right now. There is such a thing as a flooded evaporator. I don't want to get into this a lot because this gets into more chillers and things, but I do want to at least acknowledge that there is a flooded evaporator and a dry type evaporator. Most of the ones that we're dealing with are dry type, which means that by the time the refrigerant leaves the evaporator, it should be dry, meaning that it's, all the liquid's gone out of it. And then a flooded evaporator actually has liquid in it at all times. It stays basically full of liquid, or a certain percentage stays full. And then it uses another type of device. A lot of times it uses what's called a float valve, which keeps the liquid level in the coil at a certain level, which allows it to absorb heat a little bit of a different way. Usually we're absorbing it from water in that case. So you got a chiller that's circulating water through a building to cool the building, and then we're just going to cool down and remove the heat from the water. So that barrel is flooded with refrigerant, and then before it goes to the compressor, there's a float, and there's some other things in there that's going to keep that liquid from making it to the compressor, so it could still enter the compressor as 100% vapor. So a little different setup. Not going to get into that a lot, but I do want you to at least know that it does exist and that they're not always just like this one. So as a general rule of thumb, if your superheat is low, if you're adding refrigerant, let's see, if you're adding refrigerant, it's going to drop superheat. And if you're removing refrigerant, it's going to raise superheat. Now, that's not saying every time the superheat is low or superheat is high, you should add or take away refrigerant. But I'm just saying, if you got 30 degree superheat and you've done everything to determine that it's low on charge, as you add superheat or as you add refrigerant, that 30 should come down. Frost on the evaporator. So this is something else that you might run into. On air conditioning, there should never be ice on the evaporator. It should operate at 40 degrees or thereabouts, and then you're going to be running another 10 degrees superheat on the coil, on the metal. So by the time it leaves, it should be 50 degrees. So there's really no reason that you should ever have to have a freezing coil. So what can cause freezing coil usually is low airflow, dirty filter, dirty coils, fan kicks out, um, something like that's causing that going on. Doors off the unit, you left it off while you were working on it. Um, but when you get into low temp and medium temp applications, so coolers and freezers, they're going to freeze because they're going to operate under freezing anyway. A cooler is 40 degrees. You're running a 20-degree evaporator, so obviously it's going to frost. So you have to run some sort of defrost cycle in that, and then in a freezer, you're under freezing all the time, so it's going to freeze for sure. So you have to have defrost in that, and they're different. So we'll get into that in your 200 class next year, next semester. But for now, just you don't want ice. All right, so that's about all that we got to deal with right now. So hopefully that explains evaporators a little bit better to you. Um, there'll be a quiz on this, so you can get on and check that out when you're ready. And condensers will be next.